3. Check the microphone settings. Okay. 5, 6, 8. We're getting there. 9, 10. Okay. So, new lesson of probabilistic robotics. So in this lesson we will review some concepts of the factor graphs. We will present a complete example of least squares estimation in SLAM, and we will provide a wrap-up, because we're coming to the end of all the things that we have done and how to put them together and how they connect to each other. And hopefully I have time. I will present one exercise of exam-like exercise of least squares. All right. So I will briefly recap what we have said last time on factor graphs, and then we will proceed immediately to a coding example. Coding example that I think I have still to push. Let me see. Just to prevent typing the password clear. All right. So here we go. So last time, in the second part of the lesson, we introduced the factor graphs. Stemming from this, so why do we need to do so? Well, because in the context of state estimation, which is in the end the area of our course, we observe that many inference problems require the estimation of a very large number of variables, and that are connected by an equally large number of measurements. However, the measurements typically depend on only a subset of the variables in the state. And this gives to our estimation problem a lot of structure. Like these examples here introduce, so that we have seen, like post-graph, post-landmark, are examples where a variable, where a measurement depends only on a couple of things: the observing robot position and the observed landmark, or the observed being robot position and the observed robot position in case of pose graphs. And this is basically what I said in the previous slide. Whenever we have this partial observability, that means that the measurement only depends on a few things, then this means that our problem will have an inherently sparse structure. Typically, we can boil down every least square estimation problem as the estimation of the minimum of a function of this sort, where we just want to minimize the log likelihood of a set of error functions, which are typically the difference between the prediction and the observation and the measurement, that one has given a particular assignment of the state variables x. What we find out is that we could highlight the sparsity of the problem just by writing this minimization form in a canonical way, by first defining the state variable, the state as composed by a bunch of variables, not equally all belonging to the same domain, that will go from 1 to n, for instance. And then we might define the error function, which we know to be correlated to the prediction function just by a minus or a box minus with the measurement, as depending from a subset of state variable, a subset k, to denote that this is the measurement k, of the global variables in the state. This xk is nothing else than a subset of all of those over here. In case, for instance, of a post-landmark measurement, this k will have dimension 2, and here we will find a robot position, and the second variable will be a landmark position of the observed landmark. Okay. Interestingly, this error function in general can be bloated up. Each of these error functions can be bloated up to depend from all state variables, only that some of the state variables will not have any effect on the error function. But this will ensure that our mathematical derivation is consistent later on, and we have seen it already in case of multi-post registration. By doing so, recall that this k only is a subset of the state variable indices, we could consider drawing on a piece of paper the structure of our problem. And we can do this by, if we do so, we will have a factor graph where each node will correspond either to a variable or to a measurement. The variables are components of the state, clearly, and the measurements are connecting the variables from which they depend. I remark that in general a measurement does not only connect two variables, as in this example here that illustrates a post-landmark problem, but might connect multiple variables, which are all the variables of the state which are required to calculate that prediction. Okay. Interestingly, once we do this graphical representation, we observe that the graph is bipartite, meaning that one can reach a variable node from another variable node only passing through a measurement. You might observe that while in the previous slide I was showing a post-landmark problem, where a multi-post, multi-landmark problem, where the only measurements we had were landmark measurements, which means the relative position between me, robot, and a point. Indeed, we augmented this problem by adding, for instance, an odometry. An odometry that connects consecutive robot positions. And the odometry in this language can be seen as a measurement that could be predicted between by considering one robot position and the next. Okay? What could we do in this representation if we would have, for instance, a GPS? A GPS is a localization system, but we could imagine it with some sloppiness as if it was a sensor, and a sensor that depends on how many variables of the state. Well, it depends only on the current robot position, because the GPS tells you where you are. It doesn't care about where you were before or where you will go next, right? All you need to get a GPS measurement is to know your location, and then you could predict the GPS measurement. And in this case, how would we add these GPS measurements to this graph? Well, how many variables are influencing a GPS measurement? One, just the robot position. So the GPS will appear as a box here that depends on just one single variable. Okay, and it will be corresponding to an error factor in my minimization function. In my log likelihood was xk set will comprise only the current robot position from which I gather the GPS measurement. If I don't get a GPS measurement from a certain position, I will not simply add the GPS measurement to that position. Okay? Now, highlighting the sparsity, which means that not all nodes are connected with all others, leads to a consideration on the structure of the Jacobians and not the linear system. We have already seen that if an error function depends on a subset of variables, only the blocks of the Jacobians of this error function that are related to the connected variables will be non-zero. All the rest will be zero. During the construction of the quadratic form, therefore, we will have a number of non-zero blocks in the H matrix, which is equal to the square of the numbers of the non-zero blocks in the Jacobian. In classical problems, especially in SLAM-like problems, the number of new measurements that one introduces at every new robot position is bounded, is limited. This will result in adding a number of new blocks to the H matrix, which is equal to, at most, the number of new measurements that I acquire at a new time instant to the square, but this number is fixed and is limited, so it could be upper bounded. So for each robot position, at least, I will add a new certain number of non-zero blocks to H. This results in the fact that while by extending the state with a new pose variable, I will in general add, I will increase the number of elements in the matrix quadratically over time because it's a square. I will, however, fill at most a constant number of these blocks at a time, resulting in a structure of the H matrix which is more and more sparse. So where I have more and more non-zero blocks as I proceed. And this observation is a key observation because everything results like the solution of the least squares problem is normally computationally limited by the solution of the linear system. Now, to understand why, when we solve how a machine solves a linear system, especially a linear system having the sparse and symmetric structure induced by the H matrix, we would have to look into MATLAB or into Octave, and we would figure out that the linear system is solved by factorizing the matrix H. That means turning the matrix H into its Cholesky decomposition, which is composed by a lower triangular and upper triangular matrix, and then solving the system in two steps. First, solving the inner part by obtaining an unknown set of variables y, and then solving the upper part by obtaining a new set of variables delta x by knowing the solution of y. Observe that the solution of these two linear systems will be boiled down in the solution of triangular system, which are the easy ones to solve, that can be solved by respectively by backward substitution and forward substitution. Okay? Yet we have to consider that the sparse structure of H does not imply a sparse structure of L. And typically these problems are very large. And if I have a million landmarks, well, I would have a million times a million size matrix, which will be huge, and I could not even store it in memory, which means that I will not be able to solve the linear system in a reasonable time. Okay? The game is therefore to solve the system and to obtain Cholesky decomposition which is sparse. The key to do so lies in the calculation of a right ordering of the variables into the state vector. Clearly, an ordering doesn't change at all the meaning of the problem, because it's just like if you swap variable 1 and variable 2 into a linear system, and of course you apply the appropriate operation on the system matrix and on the coefficient vector, you will have the very same problem. Okay? Therefore, we might introduce a permutation matrix, and we might say that if someone gives us an ordering of the variable that is that guarantees us that the sparsity is preserved while moving from H to L, then we might have a new easily solvable sparse system. Now, having introduced a permutation matrix is nothing else than a special case of a orthonormal matrix that has the properties that I highlighted here in the slide, where the elements are either 0 or 1, and then and you have exactly 1 0 non-zero for each row and exactly 1 non-zero for each column, right? Being a special case of an orthonormal matrix, because all vectors are orthogonal to each other beside themselves, results in the fact that the inverse of a permutation is equal to the permutation. Now, knowing the ordering, we could construct a permutation, and therefore we could apply this permutation to the system. One possible way, like one way on how this could function, is to multiply both elements of the linear system to the left and to the right by the permutation and obtain a new linear system. Then we could introduce in the middle an identity that can be factored in the permutation time it's transposed, which is its inverse, in fact. Then we could end up in a new linear system consisting of a coefficient matrix H prime and a coefficient vector delta X prime, which are related to the previous one just by the reordering, and equivalently we do the same for the coefficient vector. We solve the new reordered linear system. We obtain a potentially sparse Cholesky decomposition for this linear system that is obtained thanks to the perturbation, and then at the end what we do is that we undo the effect of the permutation to have the variables right where they belong. Okay? A smarter solution could be to pre-calculate the permutation at the beginning and to reorder the variables once. It's interesting to note that given that the permutation depends only on the fill-in of the H matrix, so on the structure of the H matrix, not on the values of the H matrix, not on it. With structure I mean the structure of the non-zero blocks. One could calculate this permutation once at the beginning of the iterations and then leave it unchanged, because this permutation will result in guaranteeing us the sparse structure of L over the next rounds. Okay? We have seen on paper an example on how solving a linear system or calculating a triangularization of a linear system that was consisting of an upper arrow leads to a dense system, and we have seen on how applying such a permutation, like swapping the first row and the first column, the first and the last row and the first and last column, would result instead in a system, in a factorization which is sparse. Sparse is good because this means that we have to do less calculations and we can actually resolve this problem. Otherwise, we could not resolve it. Okay? And this was basically the key of the last lesson. Now, to give you an insight on a potential way, a very intuitive manner on how an ordering is calculated, you could just like think, and this is an offside topic of the course, so something I will never ask in the exam. A simple way is to choose first the variables that have less non-zero blocks in the actual factorization of the system. That is, you take your system matrix and you pick up a variable that has less blocks on the current row or equivalently on the current column because it's symmetric. But let's look at an upper triangular system. So now, in the if you do so and you choose to factorize, to eliminate the variable that first that has a lower degree, which means that has a lower number of blocks in that row, you could eliminating these variables would result in connecting, in filling in all the variables in the subsequent rows that have non-zero blocks on the where the eliminating variable has non-zero blocks. Just like to imagine that, I will now take paper and hoping that the light conditions are appropriate. Let's see if this works. Let's say that we have let's say that we have a linear system which has the following structure. Better. A linear system that has the following structure. Okay, our goal is to, so this is my system matrix. I just painted the fill-in. Now, our goal is to choose which variable would be the best to eliminate. Now, if we would choose this variable over here, so the first one, what would happen is that by clearing this row, we would make everything denser and denser and denser and denser and denser. And this doesn't really work. So what we could do instead is to think, hey, what is the variable that is convenient to eliminate? Reasonably, having such a linear system, a good choice could be any of the variables here, or even better, could be this variable over here. Because by eliminating this variable first, which means flipping the two, right? So if I choose this variable as first, and then I put it here, right? And this means also that I will have to swap this first row and first column, and the first row and the second column. I will end up into a linear system which has the following structure, right? How did I choose this? Well, this variable here has degree 2. This means that this variable here comes at degree 2. Why? Because on this variable I have only another element along this column, or equivalently another element along this row. Okay. In contrast, this variable here has degree n, because the first variable is full over all this line. So all these elements over here are full, and being n the size of this line, well, then I will have n elements, right? So all variables so far have degree 2, because this one here has one element here and one element here, this variable here has one element here and one element here, and so on, despite the first that has degree n, right? So I might choose any of the variables that have degree 2. Let's, for simplicity, pick up the last one. Okay? If I pick up the last one, this means that I swap the first and the last, and I proceed eliminating these at first. By doing such an elimination, given that here I have a sequence of zeros, I will not introduce any sort of fill-in. And what I will be doing, by repeating this variable over and over, but observe that I don't need to repeat this variable, I don't need to do any operation if this column here has already a 0 in front. What will happen is that I will repeat the fill-in that potentially was in this point in the bottom part. Okay? Having done this, I have automatically shrunk my system to, like, sorry, this is not a line. I have shrunk my system because I removed the first line. At this point, the question is, like, which other variable do I choose for elimination? Well, all these variables over here appear to have degree 2, so I'm fine. I can pick up any of those. In this case, I'm not stupid. I just pick up the one that it's hanging there. I proceed with the elimination, and I will go down, and I will be preserving the sparsity. Now, what happens if the structure of my linear system was something like that? Hopefully it's visible. Yes, I think so. Which variables would we choose for the elimination? Observe, this variable here, at the moment, has degree n. This variable here has degree n minus k, this variable over here. And all these variables from here to here, which are those, have degree those have degree 2, and those have degree 3, because the degree of this variable is 1, 2, 3, so the number of non-zero blocks along this line. So it would be perfectly reasonable to choose first the variables in this chunk, which have degree 2, and this will introduce basically a nearly zero filling. Then we would choose all the variables that have degree 3. Then we will choose the variables that have degree n minus k, which is this. And then the last one that we will factorize is this one over here. Observe that while eliminating a variable might introduce fill-in, because let's assume that I have a linear system that has a structure like that. Like typically they are dominant, so diagonal dominant, and then there is always a diagonal. Of course, that's always the symmetric thing. Now, if for any reason I would choose to factorize this variable over here first, or this first, this will result in moving the last one at the end and this one on top, right? So it will result in having a linear system that has this structure over here. and then all others stay. Now I don't know how many they are, but like you can imagine, because I exchange this one over here and this one over here, so I will have to flip this way and to flip this way. Okay. Now, while I proceed with the elimination of this variable, it's true that I will not introduce any fill-in down because everything is 0 here. But I will for sure introduce fill-in. I will for sure introduce fill-in in this part over here, because this line here is gonna be repeated along the parts where this part here is non-zero. So I will increase the degree of this variable. I will increase the degree of all variables that are staying like in this part. Okay, so each time you eliminate a variable, you automatically connect it to all other variables that were connected to it before, and you make a full block. So each time at each round, your game will be to pick up the variable that has currently the minimum degree. And each time you eliminate a variable, you are gonna, in general, altering the degrees of the variables that are in the graph. And therefore, you will introduce potentially new fill-in. But if at every point you choose the variable that has the lower degree, so that makes the least damage if eliminated, then you end up to a reasonable ordering. Okay, this is the idea behind the reordering of the how to get a permutation. And observe that for doing this calculation, I only had to know the structure of the linear system. I didn't have to know the values. So the degree of the variable is the number of blocks that are in that row or in that column. Okay. This was to give you an idea on why the. Oh, so I am upside down. Magic of OBS. Of how the ordering can be obtained. There's an excellent paper of Edwin Olson that explains in a very clear way these orderings, and then if you are interested, there is colmod ordering, column approximate minimum degree ordering, that are all variants on the topic. Okay, but recall sparsity is important. Now, having said so, you should know that Octave realizes, or MATLAB realizes on its own when a linear system is sparse and chooses the best method for the sort of system that you have. Now, having introduced the mechanism of factor graphs, and having realized that with this mechanism we could easily plug and play components, plug and play state variables and measurements, we could introduce a snippet of code basically that summarizes all our 3D findings in this second part of the course. This has to be seen as an example of using the methodology, which is in the end the very same methodology of least squares, while also taking account the sparse structure of the problem. Okay, so we will now go into code soon, and we will try to assemble a solver that can deal with pose problems. So like we want to estimate a map and a robot trajectory of a robot that is equipped or not with a sensor capable to measure the relative position between pairs of poses or subsequent poses in case of odometry, is equipped or not with a landmark sensor that is able to reveal the global position of a point with respect to the robot, and is equipped or not, because we will be able to switch on and off this component, of a landmark of a camera, a projection sensor that is capable to sense the image projection of a landmark with respect to the certain robot position. Okay? We will follow the classical methodology, and we will think about first qualifying the state, which in the factor graph language defines the orange blocks representing the variables, the orange nodes, and then we will proceed by defining the error functions that qualify the factors in the graph, the factor components. Okay? So, what will be the state of our system? This is a question, and I'm not moving from here until you don't have answered. What will be the state of this large estimation problem? I'm waiting. There is a latency, I know, but there is still no answer. I want to estimate the trajectory of a robot moving in 3D and the set of 3D point landmarks. Hello? Is there anyone there? Tiziano? Barbara? Are you alive? Just to check for the latency. Okay, the question is, what is the state of this estimation problem? Emanuele asks, can you repeat the question? What is the state of this total least square estimation problem? I want to estimate. I have a robot that moves in an environment, has an odometry or has a Pose-proj sensor, and it's capable to see certain landmarks. It can observe them either by a camera or by a 3D Pose sensor. Yes, but yes, Andrea, you're fine, only you missed the dimension, is SE3 object. Yes. Okay, so the state in this case will be exactly the same as the state of multi-point registration, where I have a collection of SE3 objects and a collection of 3D points, which are my landmarks. Okay? Now, I will not therefore repeat all the formalization that we have made for the state, because we have already made it when we were talking about multi-point registration. But for completeness, I will just put the slide somewhere. No. Here. Slides. The state is this. Is consisting of a collection of robot positions and a collection of landmark positions, where the robots are SE3 objects and the landmarks are 3D points. Having defined the state in this way, we could define the perturbation vector as a vector consisting of 6n being n the number of robot positions, plus 3m being m the number of landmarks, blocks, variables. And each of these blocks has the dimension of the perturbation of the corresponding variable. Okay? And equivalently, we could define the box plus as the box plus of the perturbation vector as the application of the perturbation vector of the pose to the respective pose, and the perturbation and the sum of the perturbation vector of the landmark to the respective landmark as as done in the usual way. And this is definition of the box plus, where the robot position is to each robot position is applied the corresponding perturbation through the V2T, and to each landmark position it's applied the corresponding perturbation to the traditional plus. Okay, this is the definition of the state, and I will close with that. Now, having defined the state, we have to define the measurements, right? The measurements come in 3 forms, right? Because I have 3 different sensors. The first sensor is a okay, Martina, I will answer to you in a second. So we have 3 sort of sensors. First sensor is a pose landmark sensor that is capable of revealing the relative position, the 3D relative position of a landmark with respect to the robot. Okay. The corresponding measurement will be therefore Euclidean, so no need for box minus. The measurement will be qualified as an element of R3 because it's a landmark, and the prediction function will be obtained by knowing the position of the landmark, by knowing the position of the robot, and by expressing the position of the landmark in the reference frame of the robot. Now, in this particular exercise, I wanted to parameterize the positions of the robot in the world, so XR, not as the position of the robot expressed in the reference frame of the world. Till now, we have always done the opposite. Till now, we were always talking about the position of the world with respect to the robot, because in this way we were saving us from performing the inversion. But in this case, we have to agree on a representation because we have several problems, and I find it more intuitive talking about the position of the robot in the world, because we are mixing and matching things. Okay? Now, let me 4 coordinates for the robot. Martina, okay. Martina says, in a 3D environment, you think that 4 coordinates for the robot plus 3 coordinates for each landmark. Martina, you're probably, it's not completely wrong, but you're probably thinking about a robot that moves in a surface. So if the robot moves in a surface, actually the surface is a surface, and the minimal number of coordinates could be just 2 for denoting the point on the surface, the curvilinear coordinates, and another one that denotes the orientation, right? But if we are in 3D and you just think about a quadrotor has a 6D, the position of a quadrotor is is a full 3D object. Now, let me go back to the explanation of the pose landmark constraint or pose landmark measurement. We have to calculate the prediction. The prediction of a pose landmark with this sensor will be just the pose of the landmark expressed in the reference frame of the robot. And so what we could do straightforwardly is to take the position of the robot, invert it, and multiply it by the position of the landmark. And this will give us the position of the landmark expressed in the reference frame of the robot, which is exactly what our sensor measures. Okay? And this, if you expand the formula, comes out to be the transpose of the rotation part of the eth robot variable that multiplies the difference between the landmark position and the translation part of the robot position. Okay? This is my prediction. Having the prediction, I could calculate the error function at the perturbation from the by taking the prediction at the perturbation and subtracting it, subtracting from it the measurement. Okay, and so far I'm happy. Here we highlighted the fact that the plus in the landmark word is just is not a box plus, it's just a simple plus, but it's only a implementation detail, just to highlight that in this case the landmark is Euclidean. Okay, and then you can proceed and calculate the Jacobian of this error. Calculating the Jacobian will require some calculations. I have done them in the code. I will not redo them here. This Jacobian will be consisting of two blocks, one block for the robot part and one block for the landmark part. The Jacobian will have a size 3 and so a number of rows 3, and the two blocks will have respectively 6 columns for this one and 3 columns for this one, because this object here has dimension 6 and this object here has dimension 3. Okay, and I have qualified the pose landmark factor, in fact, because this is an error function. I could do the same for the pose projective constraint, which is exactly the same, or it's very similar to the pose landmark constraint, with the difference that after taking the landmark and expressing in the robot frame, I have to take this measurement, multiply this quantity. I have to multiply this quantity by the camera matrix, and I have to perform the homogeneous division to get rid of the third component to basically consider the perspective effect. Okay, the pi is the homogeneous division that you have seen in projective ICP, where you take a vector and you divide the first element by the last, the x by the z, and the y by the z, and this gives you the image coordinates. Okay. Clearly, the projective measurement is an underdetermined measurement. So, if I observe the projection of a landmark, I cannot tell where the landmark is or how far it is. The last constraint that we will consider is the pose constraint, which was of which we talked extensively in the previous lesson, and we will see here in action. Here we summarized our findings on the pose constraint, and this gives us a 12-dimensional, because we are using the chordal distance. This gives us a 12-dimensional error vector, which is the flattened version of the transformation matrix obtained by expressing the robot position j in the reference frame of the robot position I. The error is just the difference between the prediction and the observation, and the Jacobians follow and have been expanded in the previous lesson. Okay? Now we can put all these things together into a unique problem, which is sharing the same state representation, and have fun switching on or off the different parts of this optimization. It's very important that you observe that both the pose projective problem, where you have landmarks observed by robot camera, and the pose landmark problem share the same structure of the state space, because in both cases I have robot positions and landmark positions, while the pose problem only has a subset of the previous state, that is the pose part. So here in the pose problem I only have robot positions. Okay? Now, after all this talking, let's see it running, and let's see how we can put everything together to solve this problem. Actually, like, this is quite cool, because within this problem, if we consider pose odometry pose constraints that are stemming from the odometry, and pose landmark constraints that are coming from the projection, we have something which is a complicated version of the Roomba. because Roomba has a camera that looks at the ceiling, and then it has an odometry. It has also a gyro, and that's what it is doing, actually. What I suspect it's doing. Okay, I bought the Roomba mostly because I liked to have it and to look at it rather than for cleaning, but yeah. Let's now see the program. I just pushed, so you might want to pull the things. I start from the main just to illustrate the scenario where we are operating in. I recall that the first thing that you do in these simulated or synthetic problems is to construct a simulation environment by spawning robot position and spawning landmarks. Okay? So our main will proceed exactly in this way. We create a synthetic world having a certain number of landmarks, a certain number of robot position, and we define also, not to avoid some scattering, to have the things rather concentrated, we define that all the world has to live in a box of size 10 by 10 by 10. Okay? The very first thing that we do is to construct a world, so to spawn the landmarks in the world just by randomly drawing a certain number of landmarks into this box. The second thing that we do, these are global variables taken somewhere else. The second thing that we do is to populate the world with robot positions. These are the points in the world, right? We have now to generate our variables. We define our variables in the estimation process will be consisting of two classes of objects. One will be the robot positions that we decide to represent as transformation matrices, which are 4x4 objects, and we will have num poses of those. Therefore, this is a three-dimensional array in octal. And for the landmarks, we will represent the landmarks into a matrix of dimension 3 by num landmarks. And at the beginning, we say that the landmarks are in the ground truth. Okay? Then we have to initialize the problem. We set the first robot position to the identity just because we need an origin, which will be in the middle of our box. And then we generate num poses, 10 or 9, positions at random inside this box. Like, to do so, we sample a translation vector inside the word, and we sample 3 angles between minus pi and pi, or between 0 and pi, I don't know, between 0 and pi. And then from these angles we generate the poses with the V2T. Okay? And we are done with the generation of our robot positions that we will call XR true, because this is our ground truth. Having done this, so now we have put our robot positions, we have put our camera, our landmarks, now we need to generate the observations. To generate the observations, we proceed by first generating the landmark measurements, then generating the landmark projection measurements, and then generating by generating the pose measurements. Let's in this program, I assumed that you can easily modify it by encoding the fact that not all robot positions necessarily observe all landmarks, right? Therefore, we need on the one hand a vector of measurements, and on the other hand we need a vector of associations that tell us which pose corresponds to which pose and which landmark a landmark measurement is generated from. Okay? So, in this example, I just make that all landmarks are visible from all poses. But by playing with the association vector, you can also eliminate some. So we will have ZL, which will be a 3 by num measurement vector containing the different measurements of that the poses do at the landmarks. And then we will have a vector that we call landmark associations that will be a vector of indices where the first index corresponds to the observing robot position and the second index corresponds to the observed landmark position, and it has the same size of the measurement vector ZL. Okay? So what I do here is simply iterating over all possible poses, iterating over all possible landmarks. For each pose I take the pose, I compute the inverse, because we said that in this problem we express the state variables of the robot pose as position of the robot in the world, not position of the world with respect to the robot. And so I compute the inverse only once and not in here, because it will stay fixed in the loop. Then I iterate for all landmarks. For each landmark I extract the landmark for the lambda matrix. I assemble the association vector by adding a pair of indices corresponding to the pose and to the landmark, and then I construct the measurement by multiplying the inverse of the robot pose that I call XR here by the landmark position. So this is take the landmark, rotate it of XR, which is actually the inverse of XR, and sum to it the translation part. And I increase the number of measurements. This is for the generation of the landmark measurements. I do the same to generate the projections, right? So, to generate the image projection, I will have to do exactly the same mechanism, only that in case of image projections, not necessarily I will be able to observe all landmarks, because some landmark will fall behind the camera, okay? So what I do is I assemble, I prepare to calculate the number of measurements which is equal to the total number of number of landmarks times the number of poses, just because I'm fixed with pre-allocation. The measurements will be stored in a matrix which is 2 by the number of projection measurements. Remember that the projection is dimension 2, and I will similarly have a vector of associations that I call projection associations, which is equivalent to the other vector of associations for the landmarks, only that in this case the corresponding measurement will be a projection. Then I iterate for all poses, I iterate for all landmarks. Then once I have a landmark, what I want to do is I also try to do a projection with respect of this landmark with respect to the certain robot position, and then there is a funky function which I call project point that returns two things. I think that project point is defined in total least squares.m. Okay, is defined here, like takes the robot position, inverts the robot position because I have to express the landmark into the robot frame, and then I calculate the point in the word by multiplying the inverse of the robot position by the position of the landmark. Then once I do that, I know immediately by looking at the third component if the landmark falls behind the camera or not. If it falls behind the camera, I return a -1, which is an invalid vector, means don't consider this point. If everything goes well, I take the point, I operate the projection, I pass it through the camera matrix, and I perform the homogeneous division. Like I calculate the inverse z, and I multiply the point by the inverse z. Once I've done that, I have projected my point into the image plane, but I'm not content because the point might fall out of the image plane, so I have to see if the point is inside the camera field. So if its coordinates are between 0 and the number of columns and between 0 and the number of rows. And if everything goes well, I return the point. So the error condition is that these two numbers are -1. Then let's go back. No. Let's go back to total listed squares. What I do is to calculate the projection. Is the projection good? Yes or no. If it's good, I add another association to my association vector, and I add another measurement, which is a 2D measurement, to my measurement vector. And I increase the number of measurements. Remember that at the beginning I pre-allocated a vector to be the measurement to be equal to number of poses plus number of landmarks, but this procedure might return me a number of measurements which is lower, because some of them fall at the end of the camera, and so here I do the clipping, so I cut the remaining part of the vector because it would be meaningless. Okay? Finally, the last part of my problem, of construction of the problem, will be the assembly of the pose measurements. So I decide to have only an odometry here. So as a consequence, I will use I will introduce an odometry measurement only between subsequent poses. Okay, so I will have a number of pose measurements, of odometry measurement, which is equal to the number of poses -1, because it has to be in between. So for each poses, beside the last, calculate the previous, calculate the next, and then add to the pose association a pair of indices that denote current and next pose, and add to the measurement vector, that will be a matrix in this case, inverse of xi multiplied by xj. Okay? And this is the construction of the problem. At this point I have all the fantastic measurement where they should be. I have all the fantastic landmarks and poses where they should be. Now I need to make it dirty, so I need to add some sort of error to my estimate, because otherwise I would be solving the problem at the origin. But I strongly recommend you to start, when you do your development, to start from a zero error configuration, because if then the system explodes with a zero error configuration, you might start debugging at that point and not later. The sooner you start debugging, the quicker you find the error. To do so, we now need to apply a certain perturbation to each pose. So we're not adding noise, we're just moving the robot positions a little bit from their ideal initial guess location, because we want to then find them after the optimization at the ground truth. And so we add to each variable of my state, that will be the variables where I'm operating, which is robot positions guess and landmark position guess, we add a perturbation to each pose. And we do the same for each landmark. Okay? So what I do here, I take a pose, I calculate a perturbation as a V2T object, and then I apply this perturbation to the corresponding variable. And here I can do this in a bulk operation by calculating a generic perturbation for the landmarks as a matrix, and then summing this matrix to the landmarks in my state. Finally, I can call the solver, and in calling the solver, now we will see how it's constructed, this funky solver. Now, I might decide, if I want, to delete some measurements. I might decide to eliminate, for instance, the landmark measurement, or I might decide to eliminate the projection measurement, or I might decide to eliminate the pose measurements of the robot. It's quite interesting because if you just give a zero vector, like a zero vector for the landmarks or for the poses or for the robots, the corresponding measurements will not be considered. The corresponding factors will not be considered. Okay, because there's nothing in the summation that will contribute to my H matrix. This fantastic function takes as input, which is called do total ls, takes as input the current state, takes the landmarks and the landmarks associations, takes the projections and the projection associations, take the post-pose measurement and the post-pose association, takes the number of iterations, takes potentially the damping, and takes potentially a kernel threshold. That is the kerneling that we might want to do in certain parts. Now, how will this total ls work? Let's see. Okay, total ls will do least squares, right? And by doing least squares means that I have to, for sure, implement the box plus operator. The box plus operator is implemented, and it's copied actually from the box plus of the multi-pose registration problem. The box plus in this class of problem takes the number of, the robot position, takes the number position, the landmark position, takes two useless variables which are number of poses and number of landmarks, and takes a perturbation vector dx that consists of all the perturbations in the thing, in the pool. What you need to do is the usual bookkeeping of the indices. For each pose in the pose vector, you have to retrieve where this, the perturbation of this vector starts in the perturbation vector by using the famous pose matrix index that we have introduced in the context of multi-pose registration, and we extract this perturbation part, and we compose it with a V2T to the corresponding robot position. And we do the same for the landmarks. I'm going fast because we have already seen this piece of program both in the slides and in the multi-point registration problem. We do the same for the landmarks. Okay? Now, I said that these two variables are useless. Yes, because these two elements over here could be beautifully desumed by the XR and the XL thing, right? And given that I can't stand useless code, this is exactly what I'm gonna do. XR3. XL2. The size is already encoded in the structure of the landmarks and the robot pose, right? Because I know how many matrices I have in the vector. Okay. Very good. Of course, I will have to change it later. Now, this is the box plus, and my beautiful do total ls function. Oh, thanks God, I don't have num poses here. Very good. My do total ls function will be responsible of doing the following thing: taking the current state, taking the landmarks, taking the projections, take the landmark measurements, take the projections, taking the robot measurement, taking the number of iterations, and repeatedly solving least squares, which means calculate the quadratic form, solve the quadratic form, and apply the increment. What this function will return is the updated state, and then I will have also statistics, the statistics of the landmarks. So what is the chi-square contribution of the landmarks, and how many layers I have in the landmarks. What is the chi-square, the error of the projections, and how many projections I have, and the statistics about the robot, the post-pose measurements, and how many in-layers do I have. And also H and B in case I want to show or to do rank considerations, which I might want to do later. Okay? And the system is rather straightforward. For each iterations, you can resize the H matrix and the B vector. the system size is just the dimension of the perturbation vector. If you have landmarks, because if you don't have landmark measurements, well, the landmark will not appear in the state. That's the only difference. But if you have landmarks, then you will update the H matrix by adding the contribution of by computing the quadratic form based on the landmark. We will see this later. This is the classical quadratic form that we have seen in multi-point registration, and we will see in a while. But it should be clear that in this case, this function here takes the robot position, takes the landmark positions, takes the landmark measurements, and takes a kernel threshold, and constructs an H matrix and a B vector, and also updates the key and the number of inliers based on the data that you feed into it, and then you update the key stats and the number of inliers. Similarly, we will construct the contribution of the linear system into another H matrix, which we call H projection B projections, just to make it more confusing, and we construct we build the linear system for the projections, right? Yeah. Jesus, I mean, I can't stand it. Yeah. I can't stand it because these variables are redundant. I mean, it would be much better to do this. I had to do this because if I was using a proper programming language, I could have passed by reference the matrix into this function and get the matrix modified inside the loop. Instead, I have to return it and sum it. So that it's BL. Okay? Makes more sense to me. I hope you understand what I'm doing. If we have landmarks, we will have a landmark contribution. If we have poses, we will have a pose contribution. Okay? And at the end, I have a generic linear system. I compute the perturbation, and I apply the perturbation to the previous state with a box plus. Okay? Now, I'm curious to see if what I've written runs. Known poses, yes, undefined. That is. Okay. In the attempt of cleaning the thing, I made mess. undefined. Why? Sorry, guys. No? What did I do here? What a terrible thing. Let's revert and live with the useless variable. Okay. Probably I made some wrong bookkeeping. But I know it. The problem was here. If you change a function, you have also to change the invocations of a function. Fine. Okay. That was my problem. So I could revert everything and go back to the clean formulation that I provided you. But I missed it.